to measure those chemical reactions, we're going to use a calorimeter. Okay, now we can do constant pressure calorimetry, which means that atmospheric pressure is going to be constant. Now we're going to assume also that no heat is lost to the surroundings. So going back to our coffee cup calorimeter, we have inside the coffee cups are a system. That's where our chemical reaction is going to occur. Styrofoam cups are acting as insulation, so that's our boundary. Outside that cup is our surroundings. We're going to assume all the energy transfers stay within that cup. And then we're going to put a thermometer in there to measure that temperature change. And keep in mind, with measuring that temperature change is not a measurement of heat. So keep this calorimeter picture in mind as we look at an example of this. So let's say I take 50 milliliters of a 0.1 molar silver nitrate solution and I mix it with 50 milliliters of 0.1 molar HCl solution inside those styrofoam cups. I then measure my starting temperatures of both those solutions, and they start at 22.30 degrees Celsius. At the end of the reaction, the final temperature reads at 23.11 degrees Celsius. So I want to calculate delta H for the reaction that just occurred. Now, one thing I have to note is I also have to know something about the calorimeter, and I have to know the heat capacity of the calorimeter. So we're going to assume the heat capacity is 35.7 joules per degree Celsius. If you're not given any information about the calorimeter, what we'll do is assume that the calorimeter doesn't play a part in this process. We don't have to worry about it losing heat or gaining heat. Okay? If you are given information about calorimeter, though, we have to take that into consideration. All right, but before we do that, first we need to know what's the balanced equation. Well, when I write out my silver nitrate aqueous plus HCl aqueous, how do I know they're aqueous? Well, I'm saying I mix the 50 mils of the 0.1 molar solutions of each. Okay, I get silver chloride solid and HNO3 aqueous. That's me predicting my products and predicting their phases and then writing the balanced equation. All right, so what we're really trying to find is delta H for this specific reaction. Now we have to keep in mind, and we'll come back to this again, we're trying to determine delta H for this reaction. In this reaction, we're dealing with 1 mole of silver nitrate reacting with 1 mole of HCl. Now normally we'd also want to consider limiting and excess reagents. Whichever one is going to be the limiting reagent is going to determine how much heat we can produce. But in this case we have equal amounts of these mixings, so we're not concerned about limiting or excess reagent. Main thing though, when we go to calculate delta H's, we have to calculate it for the number of moles in the reaction. With this problem then, let's identify all the sources of heat exchange. So what's absorbing heat, what's losing heat? Well, one thing we know is we have the calorimeter. That could absorb heat, it could lose heat. Right? What else? Well, when we mix two aqueous solutions together, because it's aqueous, that means it's dissolved in water, right? So most of that 50 mils of the silver nitrate and 50 mils of the HCl is water. So that water could gain or lose heat as well. So we have Q associated with the water. All right, is there anything else? Well, obviously, something caused that water to heat up. What caused that water to heat up? Well, it had to have been the chemical reaction. Okay, now we know that water heated up, which means our Q of reaction is going to be exothermic. We know it's going to end up being ultimately a negative value. If that water had cooled down, we know it was going to be endothermic, and that Q value would have been positive. So once we've identified all those sources of heat, we can start thinking about how are we going to calculate Q for each. Well, Q the calorimeter, because it's an object, we're going to use heat capacity times the change in temperature. For the water, because it's a compound, we're going to use the MS delta T. What about Q of the reaction? That's what we're actually concerned about. How are we going to calculate that? Well, that goes to looking at that equation we set up where we add up all of those heats and set them equal to 0. If I have Q the cal plus Q the water plus Q the reaction equal to 0, if I solve for Q the reaction, it's going to be equal to the negative value of Q the water plus Q the calorimeter. So Q the reaction is what I'm trying to solve for here. In order to get that, I need to know Q the water, Q the calorimeter. So let's calculate each one of those individually. Let's start with Q the calorimeter. I'm told I have 35.7 joules per degree Celsius. My temperature change, my final temperature is 23.11 degrees Celsius. My initial temperature is 22.30 degrees Celsius. Make sure you always do final minus initial. That's going to determine what sign this is going to have, and it's ultimately going to help us determine whether we have an endothermic process or an exothermic process. Right, if the 22.3 had been my final temperature, that would have gone first. So don't always put it as the biggest minus the smallest. Always look at it as final temperature minus initial temperature. Now the reason why I'm using that same temperature change as what I'll be using for the water is because the calorimeter was in contact with the water through this whole process. So we're going to assume that whatever temperature change our solutions went through is going to be the same temperature change that our calorimeter is going to go through. Okay, so I do that, calculate it, end up with 28.9 joules. All right, let's look at the water then. Plug everything in for the MS delta T. How did I get that 100 grams? Well, if I have 50 milliliters of a solution and another 50 milliliters of solution, that's 100 milliliters total. If most of that is just water, we can take that 100 milliliters and convert it to a mass. Right? How do we convert the 100 milliliters to a mass? Well, we need to know density. And the density of water is going to be 1 gram per 1 milliliter. So if I have 100 milliliters of these solutions, the assumption we make is it's mostly water, so that's going to be equivalent to the number of grams we have. So I plug all those values in and end up getting 3.39 times 10 to the second joules for the water. All right, well, that's how much heat was absorbed by the water. I now want to calculate my Q of reaction. So remember, my Q of reaction is negative Q of the water plus Q of the calorimeter. So negative of 3.39 times 10 to the second joules plus 28.9 joules. So my Q of the reaction is going to be a negative 367.9 joules. Now keep in mind, that's the amount of heat for this specific experiment. I'm trying to calculate delta H for this reaction. In this reaction, I have 1 mole of silver nitrate reacting with 1 mole of HCl. So we want to determine how much heat is produced for 1 mole of the reactants coming together. So I know for this experiment that I did, my Q of reaction was a negative 367.9 joules. But that was for how many moles of the silver nitrate? It wasn't for 1 mole of the silver nitrate, so I need to figure out how many moles of silver nitrate did I have react. Once again, this is where limiting an excess reagent would be an issue. Whichever one would be the limiting reactant, we'd use that to calculate the moles that we're going to use. In this case, they both have equal amounts, and it's a 1-to-1 ratio in the balanced equation, so we don't need to worry about that limiting an excess reagent. So if I take my 50 milliliters of silver nitrate times the molarity of my silver nitrate, I end up with 5.00 times 10 to the negative 3 moles of silver nitrate. Is that 1 mole of silver nitrate? No. So that many moles of silver nitrate in this reaction produced a negative 367.9 joules of heat. We need to know how much heat is produced for 1 mole. So in order to calculate delta H for this reaction, we take our heat, our Q of reaction, divided by the number of moles used in that reaction. And when we divide those out, we end up with a negative 7.36 times 10 to the 4th joules divided by 1 mole of silver nitrate. So we know it's a negative 7.36 times 10 to the 4th joules for every 1 mole of silver nitrate that reacts. So we'd write that as our delta H value. Now, when we write those delta H values, if we've got a large number for joules, a lot of times they're reported as kilojoules. Now, when we report this out then, we can just report it as the balanced equation followed by that delta H is equal to negative 73.6 kilojoules. We could put kilojoules per mole, but the negative 73.6 kilojoules written there, it means it goes with that balanced equation. In that balanced equation, we have 1 mole of silver nitrate and 1 mole of HCl, so we don't need to write kilojoules per mole necessarily. So let's look at a different example of calorimetry. And this time we're going to deal with constant volume calorimetry, or sometimes called bomb calorimetry. Now this type of calorimetry is going to be used typically for measuring combustion reactions. So if we look at a bomb calorimeter, what we have is a small internal container where we've pressurized some oxygen gas inside there. We've put our sample that's going to react with the oxygen or combust, and then that whole container is lowered into some water. Then what we do is we apply a spark to that container, and that starts the chemical reaction, starts that combustion reaction. Combustion reaction then produces heat. We can measure the heat produced in the water by measuring a temperature change, and then we can calculate back that heat of reaction. This particular one, we keep a constant volume, but not a constant pressure, because the pressure of the O2 gas is going to be changing. Whereas in the other calorimeter, with the styrofoam cups, that was a constant pressure because it was open atmospheric pressure.
Okay, so let's look at an example of this. Let's say I have a new sugar substitute and I want to determine the number of calories per serving. Keep in mind that's a capital C calorie, so that's a nutritional calorie. So let's say I take one serving, put it in a bomb calorimeter, ignite it with the O2, and then measure the temperature of the water, and then measure the temperature change of the water surrounding that bomb calorimeter. If I have 1 kilogram of water surrounding the bomb calorimeter, that 1 kilogram being 1 liter, and I measure the temperature change going from 22.345 degrees Celsius to 29.134 degrees Celsius, and I know the heat capacity of the bomb is going to be 5.067 kilojoules per Kelvin, I want to calculate how many nutritional calories per serving I have for this sugar substitute. Now keep in mind, I'm not looking at the chemical reaction per se. All I want to know is from one serving, how much heat am I going to get? All right, so first let's identify all the sources of heat exchange. Well, one of them is the calorimeter. We then have the water. The calorimeter and water are heating up, and that heat's coming from the reaction. So how are we going to calculate Q for each? Well, the calorimeter is the C delta T. The water is the MS delta T. And then for that Q of reaction, we've got to use that Q cal plus Q water plus Q reaction equals 0. We add up all of those possible sources of heat exchange and set them equal to 0. Solve for Q of reaction. All right, so we know the Q of reaction is a negative Q of the water plus Q of the calorimeter. So let's calculate each one of those individually. Q of the calorimeter, we plug in the heat capacity for the calorimeter times the change in temperature for the calorimeter. We get 34.4 kilojoules. Do the same thing for the water. Now we have 1 kilogram of the water, so it's 1,000 grams times specific heat of the water times change in temperature of the water, and we end up with 28.4 kilojoules. Plug those into the equation above, we get our Q of reaction is going to be a negative 62.8 kilojoules. So we know the heat produced from one serving is going to be a negative 62.8 kilojoules. Now keep in mind that negative means heat's given off in the process. Okay, so when we go to consider what the nutritional calories per serving are, we can ignore that negative. Negative versus positive, it just tells us direction of heat flow. Okay, in this case, heat was given off from the chemical reaction. So if we want to know how many nutritional calories this is, we're going to have to start with our kilojoules. We're going to have to convert it to joules. Convert those joules to regular calories, and then take those regular calories and convert them to nutritional calories. So we carry out that calculation, and we end up with 15.0 nutritional calories. So that one serving would have 15 calories in it. Okay, so this has gone through a couple of different types of calorimetry problems. Keep in mind, whenever you're looking at a calorimetry problem, always be thinking about what's the sources of heat, both things that are gaining heat and things that are losing heat. Add up all those sources of heat, they should equal 0. Then you're going to either use MS delta T or C delta T to run their calculations. These are the ways that we get these delta H of reactions. So ways that we just determine how much heat is given off by a reaction. All right, so that's going to be it for calorimetry.